ماشيين فيه. اليوم راح نتكلم عن نايكوست بلس اناليسيس عن ستابيليتي. فيصل رامدي، عبد الله الزرعه. في البدايه راح نعرض فيديو بسيط توضيحي للدرس، بعد كذا نبدا بالاكتيفيتي اللي بعدها.
Hello and welcome back to Control System Lectures. Let's cover the highly requested topic of the Nyquist stability criterion, at least the first part. This is a topic that I can honestly say I didn't really get as an undergraduate student, but it turns out that I was just being lazy because the criterion is actually pretty easy to understand with just a small amount of concentrated effort. So let me explain it to you the way I understand it, and maybe with this video and some other textbooks and other videos on YouTube, you'll be able to create your own understanding of the criterion as well. But first things first, let's talk about what we're trying to accomplish by using the Nyquist stability criterion. Here is a typical open loop block diagram of plant G of S and control process H of S. You generally have both of these transfer functions for your system since you know the plant that you're trying to control and you get to pick the control process to control it. The open loop transfer function then just becomes G of S times H of S. But to save time in this video, I'm going to drop the of s's and just write G times H. When we close the loop, this physically adjusts the transfer function for the entire system, and you can reduce the block diagram into a closed loop transfer function, G divided by 1 plus G of H. So you can determine if your open loop system is stable by finding the poles of G times H. The poles are values of S that cause you to divide by 0 in the transfer function and so that the result blows up to infinity. If there's a pole in the right half plane, then the open loop transfer function is unstable. For the closed loop system, we're still looking for poles. However, you can see from the transfer function that in order to divide by 0, 1 plus GH would have to equal 0. Therefore, we can check stability of the closed loop system by looking at the location of the zeros in 1 plus GH. This might get a little confusing because I might accidentally say, we need to check for closed loop stability by looking at the location of the zeros. But what I really mean is that just the locations of the zeros of 1 plus GH. So just keep that in mind as we move forward. So all we're really trying to do is find where the zeros are of 1 plus GH, or take the open loop transfer function, add 1 to it, and then find the location of the zeros. Why is this so difficult? Well, for one thing, if your open loop system is high order, let's say 50 poles or something, then finding the roots of that large 50th order equation can be difficult by hand. Of course, now we have computers, so that isn't a big deal. But even so, all you would have is stability information, and no other useful information like stability margins. So let me show you something real quick in MATLAB. I'll just generate a random transfer function called sys. I'll plot the locations of the poles and zeros for this open loop system. And then right next to it, I'm going to plot the poles and zeros of 1 plus the open loop system. So here you can see how the zeros in the right graph are not obviously related to the poles in the open loop system in the left graph. That's because when we add 1 to the open loop system, it can really move the poles and zeros around. However, let's generate the Nyquist plot for G times H and 1 plus G times H. Hey, this kind of looks like Mickey Mouse randomly. Anyway, isn't this much simpler looking? All we're doing is adding 1 and just shifting it over. So adding 1 to the open loop transfer function and trying to find the pole 0 locations is hard graphically, but adding 1 to a Nyquist plot is really easy to do. Now the only thing we need to know is how to determine stability and stability margins from this graph of squiggly lines. And once we know that, then we're golden. Luckily, it's pretty straightforward once you know what to look for. But before I tell you that, I first want to show you how this plot is generated. And in doing so, I think reading it and determining stability will become obvious. To start, we need to discuss Cauchy's argument principle. Let's say that we have this arbitrary transfer function, s plus 2 over s plus 1. And I'll put the s-plane on the left here and mark the locations of the poles and zeros for our transfer function. There's a pole at minus 1 and a 0 at minus 2. Now if we take just a single point in the s-plane, let's say s equals minus 1 plus j, and plug it into our transfer function, which is s plus 2 over s plus 1, you'll get a new complex number out, 1 minus j. And let me plot this new complex number on a new plane that I'm just going to give an arbitrary letter w, the w plane. This process of plugging in one complex number in the s-plane and getting a new complex number in the w-plane is called mapping. So the transfer function maps a point from the s-plane to a different point in the w-plane. And if we add a second s point near the first, we're going to get a second point somewhere else on the w-plane. And if we plugged in more and more points on the s-plane as to form a continuous line, then this will form a continuous line in the w-plane. And if you draw a continuous line that connects back to itself, we call this a contour. And it'll generate some sort of continuous squiggly line over in the w-plane that also connects back up with itself. We're going to call this line in the w-plane a plot. Except that squiggly line isn't just random gibberish. It actually contains the phase and magnitude information from each of the system's poles and zeros. Let me explain it in the following way, using just a small amount of math. But really concentrate on the idea rather than the math if you find it confusing. I'll simplify our transfer function just a bit for this example, down to a single zero at s equals minus 2. And I'll map the point s equals minus 1 plus j over to the w-plane using our transfer function s plus 2 over 1. And we find it to be 1 plus j. Now here's the really interesting part. The phasor of the point in the w-plane is exactly the same as the phasor between the 0 and the point we chose in the s-plane. And this concept extends to multiple poles and zeros as well. And what's nice is that you can figure out the mapping between the s-plane and the w-plane graphically. I'll show you how in this set of 3 poles and 2 zeros. Step 1 is to pick the point in the s-plane that you want to map over to the w-plane. Step 2 is to draw the phasors from each of the poles and zeros to that point. Step 3 is to determine the magnitude, or the length of the phasor, by multiplying all of the zero phasor magnitudes and dividing out all of the pole phasor magnitudes. This resulting magnitude sets the length of the phasor in the w-plane. Step 4 is to determine the phase by adding the phase of all of the zeros and subtracting the phase of all of the poles. So in our case, we'd add the 2 blue angles, subtract all of the orange ones, which just by eyeballing it looks like the phase would be just greater than 90 degrees, and so it would be here in the w-plane. So you might be wondering why I'm telling you all this. We aren't going to be doing this mapping graphically in general, since it's usually easier just to plug in the point and solve the equation. However, understanding what is happening in a graphical sense is going to help us interpret the plot later on. Let me show you what I mean using MATLAB again. I wrote a small program in MATLAB to give you a visualization of what I just drew for you. Here we have a transfer function with 2 poles and 1 zero. You see the exact function in the title. I've chosen a value of s right in the middle at s equals minus 2. And on the right is the mapping of that point into the w-plane. You can see very quickly that if we add the phase of the 0, which is 180 degrees, and subtract the phases from the poles, which is positive and negative of the same angle, so they cancel each other out, that the phase should be 180 degrees on the point on the right. And it is. Now let me move this point to a new spot in the s-plane. Now the phase from the 0 is plus 90 degrees, and the phase from the pole is maybe around 60 degrees or so. And therefore, 90 minus 60 is about 30 degrees, and that's again what we see of the point in the w-plane. Now if I sort of trace out a contour with this point, but make sure not to include any pole or zero, then the addition and subtraction of the phases will never go around 360 degrees. And you can see this very clearly on the W plot, that the phase just sort of hovers between 150 degrees and 210 degrees. However, if I do encircle a zero, then as we go along the contour in a clockwise direction, we'll be adding 360 degrees of phase as we move around the zero. This causes the point in the W-plane to rotate 360 degrees in a clockwise direction, like our contour. And if I circle a pole, then we're subtracting 360 degrees of phase as we move around the pole, causing a counterclockwise rotation in the W-plane. Now, I've written a second demo that might make this a little bit easier to see. Here I have a single pole that I encircle, and the resulting plot circles the origin one time in the counterclockwise direction since we're subtracting 360 degrees of phase. Now I'll add a second pole and rerun it. And as you can see, there's going to be 2 rotations around the origin, one for each pole. Finally, I'm going to add 2 zeros as well. And now the resulting plot doesn't circle the origin at all. And that's because we're adding 2 times 360 degrees of phase from the 2 zeros, but at the same time subtracting 2 times 360 degrees of phase from the 2 poles. Sure, the plot on the right, which is the green line, is still going to have a bunch of circles and squiggles in it, but it never encircles the origin, which is really important to note. And that is really all you need to know for Cauchy's argument principle, that you can tell the relative difference between the number of poles and zeros inside of a contour by how many times the plot circles the origin and in which direction. So let's see, if I gave you this arbitrary contour and then told you that the mapping in the W-plane looked like this, what could you tell me about what's inside? Well, let's see, it circles the origin once in the clockwise direction, so there must be 1 0 inside the contour, right? Wrong. Well, sort of wrong. Remember, all this tells us is that there is 1 more 0 than poles inside the contour. So if there are no poles, then there is 1 0. But what if there's 3 poles? Then there must be 4 zeros. Now let's take a new contour, and if I said that the mapping looked like this, where it encircled the origin twice in the counterclockwise direction, well, then you would say that there are 2 more poles than zeros. And if we knew that there were only 2 poles to begin with, then we could confidently say that there were no zeros in this contour. In order to figure out how this information helps us, let's get back to our problem. We're trying to figure out if there are any zeros in the right half plane for 1 plus GH, because if there are, that means that the closed loop system is unstable. And now we know how to use Cauchy's argument principle to determine if there are any zeros inside of a contour. So at this point, it should be obvious that if we want to see if there's any zeros in the right half plane, then we need a contour that encloses the entire right half plane. And we do that by saying that the contour runs the entire length of the j omega axis up to positive j infinity, and then it sweeps around at infinity to enclose the entire right half plane, and then goes back up the negative j omega line back to 0. Now if there are any zeros in the right half plane, we're going to know about them. This is called the Nyquist contour. All those other contours we drew didn't have a name, so maybe I'll call one like the Douglas contour or something. But when you map the Nyquist contour into the W-plane, you get what's called the Nyquist plot. It's all those squiggly graphs I plotted in MATLAB earlier. And again, you get those plots by plugging in every single value along the j omega axis and then all the points along infinity in the right half plane. This is easier to do than you might imagine, but I'm going to cover that in the next video. For now, we'll rely on the computing power of MATLAB to generate those plots for us. So now if we take 1 plus GH, and use this function to map the Nyquist contour in the S-plane into a Nyquist plot in the W-plane, we can instantly see how many times the origin is circled and in which direction. From there, we can determine how many more poles or zeros lie within the contour. To do this mapping, though, we need to find the plot for GH and then shift the entire plot to the right by 1. But this is kind of difficult because there's lots of curves and circles, so instead of shifting the plot to the right by 1, we shift the origin to the left by 1. And this is why we're concerned with how many times minus 1 is circled instead of how many times the origin is circled. So the steps are that we take the open loop transfer function, GH, we make a Nyquist plot by plugging in each point on the Nyquist contour and count the number of times minus 1 is encircled and in which direction. From that, we can determine how many more poles or zeros are inside of the Nyquist contour, which again is the entire right half plane. But to know for sure whether there's a zero in the right half plane, we first need to know how many poles are in the right half plane. Luckily, we usually know exactly how many poles are in the right half plane of 1 plus GH because it's the exact same number of poles in the right half plane as the open loop system GH. And since we usually have a good understanding of our open loop plant, then we already have that information. And this drives the famous equation that the number of zeros in the right half plane, z, is equal to the number of clockwise encirclements of -1 plus the number of open loop right half plane poles. Or another way of saying this is that in order to guarantee there are no zeros in the right half plane, then you better have exactly one counterclockwise encirclement for every open loop pole in the right half plane. Any less than that, and you know you have at least one right half plane zero messing things up. So one very important bit of information you should be taking away from this is that if someone gives you a Nyquist plot and asks you to tell them how many zeros are in the right half plane of 1 plus GH, you can't unless you know a little information about the open loop system, GH, namely how many unstable poles there are. Now, one thing that sets Nyquist plots apart from Bode plots in terms of determining closed loop stability is that with Nyquist, you have the ability to analyze a system with an unstable open loop plant. If you try to determine closed loop stability of an unstable open loop plant with Bode, you're going to be out of luck, because you'll possibly come away with the wrong answer and not know it. There are also other examples of other types of systems that will confuse you in Bode plot form, but will always work perfectly in Nyquist form. Bode plots are nice because they're easy to sketch by hand. However, if you have access to a computer, you won't go wrong if you always use Nyquist plots to determine stability and stability margins, and then just use Bode plots for frequency response analysis. So this is all I wanted to cover in part 1 of the Nyquist stability criterion. In the next video, I'm going to explain what to do when your open loop plant has a pole or two on the j-omega axis, and also how to determine phase and gain margins directly from the Nyquist plot. Plus, I'll give you a few examples. Now, if you have any questions or comments, please leave them below and I'll try to answer them if I can. Subscribe so you don't miss any future videos, and as always, thanks for watching. Welcome back to Control System Lectures. This is part 2 of our explanation of the Nyquist plot. In the first part of this series, I showed you the method of mapping from the S domain to the W domain using the transfer function. I also explained how to use Cauchy's argument principle to our benefit, what the Nyquist contour was, and finally how to interpret the resulting Nyquist plot. So now let me continue from there, and in this video I'm going to show you a simple way to estimate a Nyquist plot by hand. I'll explain how to handle open loop poles and zeros on the imaginary axis, and then walk through an example that illustrates the power of the Nyquist plot over similar methods like the Bode plot. So let's get to it. We'll start with estimating a Nyquist plot by hand. Let's say that I have this S-domain transfer function, 1 over s squared plus 3s plus 2, which has these two poles, s equals -1 and s equals -2. Now recall from part 1 that I need to map the Nyquist contour to some other plane that I've arbitrarily called the W plane using this transfer function. So how do we do that? Well, the most straightforward, if not silly way, is to take a point in the S-plane on the contour and plug it into the transfer function, and then plot the resulting complex number in the W-plane, just like I'm doing here in this example, where this one point in the S-plane maps to this other point in the W-plane. And we can continue this for every single point around the entire Nyquist contour, but I'm sure you can see a problem with this. Not only is this a very math-intensive way, but it also causes us to miss out on some very important intuition about how the Nyquist contour relates to the Nyquist plot. So let me illustrate a better way to plot this. First, we're going to divide the Nyquist contour up into two pieces, and then we'll address both pieces separately. The first piece can be represented by j omega, since it's just the entire j omega line, where omega goes from -infinity to +infinity. And we can map this entire segment all at once by plugging in j omega for s in our transfer function, and then sweep through all omega by plotting the resulting real and imaginary components. Also, because of symmetry of the poles and zeros about the real line, the negative portion of the j omega line is just the reflection of the positive portion, and so we really only need to calculate the positive frequencies, but I'm going to explain more about this later. The second piece starts at infinity on the imaginary axis, loops around to infinity on the real axis, and then finally -infinity on the imaginary axis again. Now I think this segment is pretty interesting because despite the fact that it is infinitely long, the entire segment maps into a single point in the W-plane. Pretty crazy, huh? But there is a catch. It maps to a single point only if the denominator of your transfer function is higher order than the numerator, and this is called a strictly proper transfer function, or if it's equal order to the numerator, and this is called a proper transfer function. If the numerator is of higher order than the denominator, then this is not a proper transfer function. And the second segment maps to a single point for only the first two and not the last. But that's okay because all physically realizable systems are either proper transfer functions or strictly proper, and that's why I'm going to focus on them in this video. You can show mathematically why that second segment maps into a single point in the W-plane, and there's a lot of great videos that do that. So instead, I'm going to quickly explain in a graphical sense why this is true. Remember from part 1 that the phase in the W-plane is just the sum of the angles of the zero phasors minus the sum of the angles of the pole phasors. And then for the gain, I didn't cover that really very well in the first video because it's a bit misleading graphically. But for our following example, it's acceptable to say that the gain is proportional to the magnitude of the zero phasors divided by the magnitude of the pole phasors. So we're going to use that definition going forward. Let's take the case where there are more poles than zeros, or a strictly proper system. It's easy to see that if you pick a point way out at infinity, since the pole phasors outnumber the zero phasors, the gain will become a very large number in the numerator for the zeros, divided by more very large numbers in the denominator for the poles. And that's going to put the gain really, really close to zero, and it's going to reach zero as that point goes actually out to infinity. And since the gain is zero, we don't need to worry about the phase because the point is always at the origin in the W-plane. And phase would just be akin to spinning your pencil in place at the origin. It's still the same point, and so we don't really have to worry about it. For proper transfer functions where you have the order of the numerator and denominator equal, you have this situation. Now along this infinity line we get a very large number from the zero divided by pretty much that exact same large number as you approach infinity. This puts the gain at 1, which remember I said was just proportional to the real gain. So all I can say graphically is that the gain is a non-zero but finite value. So somewhere out here. But what about the phase? Because it could exist anywhere on this circle, so now phase is important. Well, the angle for both of these phasors approach the exact same value as s goes to infinity. So when you subtract the pole angle from the zero angle, you always get 0 degrees, which means that this entire line maps to a single non-zero point on the real axis. So it maps to 0 for strictly proper systems, and a non-zero but positive real number for non-strictly proper systems. Now to simplify the Nyquist contour. Since the second segment of the Nyquist contour all maps to the same point in the W domain, then we don't need to worry about it when we're plotting. The point is taken care of with the positive infinity in the j omega axis. And because of the reflection, we don't need the negative omegas, so we really only need to plot the positive j omega part. Now at the risk of confusing you, I want to explain what happens if you don't have a proper transfer function. In this situation, on the infinity portion of the Nyquist contour, the gain also goes to infinity since you have more zeros than poles. And as you loop around that portion of the contour, the phase is also changing as you do that. So in this case, the portion of the Nyquist contour doesn't all map to a single point. However, this is really only a concern to mathematicians and not engineers, since engineers deal with physically realizable systems. But keep this in mind in case you come across a non-proper transfer function someday. So after all of that, let's go through the steps to generate a Nyquist plot. First, replace s by j omega in your transfer function. Second, sweep omega from 0 to infinity and plot the resulting complex numbers in the W-plane. And then finally, without picking up your pencil, draw the reflection about the real axis to account for the negative omegas. And don't forget to keep in mind the direction of the contour. Remember from part 1 that we traced the Nyquist contour in the clockwise direction. So if we start at omega equals 0, then we trace up to omega equals infinity and then continue around in the clockwise direction from there. I know what you're thinking. I've been rambling on for 8 minutes and I haven't actually told you anything about how to plot. All I've done is explain why we only need to worry about plotting the positive j omega section of the Nyquist contour rather than the whole thing. But how do we estimate the plot after we replace s by j omega? Well, the way I prefer is actually explained very well by Professor Gopal at the Indian Institute of Technology. He has a great YouTube video on it, and I've placed a link in the description if you'd like to watch the technique being explained from a professional professor, but I'm going to summarize it here. For simple transfer functions, there are only 4 points that you need to solve for, and then from there you can deduce the shape of the entire plot. The first point is when omega equals 0. The second point is when omega equals infinity. These determine the starting and midpoint of the Nyquist plot in the w-plane. The third point is where the plot crosses the imaginary axis, and the fourth point is where the plot crosses the real axis. So let's try this with our original transfer function and see what we get. For the first point where omega equals 0, we can basically just plug in 0 for each of the s's, and we're going to get 1/2 for our starting point. For omega equals infinity, we just plug in infinity for each of the s's, and we're going to get 1 over a really large number, which is 0, which is what we expected since this is a strictly proper transfer function. So the midpoint is at the origin. The third and fourth points are slightly more involved, but you can solve for them by setting s equals j omega in the transfer function, and then separating out the real and imaginary components. I've done that very thing here, albeit really quickly. At this point, to solve for the imaginary intercept, set the real part to 0 and then solve for omega. Then plug that omega into the imaginary part and solve for the value, and that's where it crosses the imaginary axis. It's a similar story to get the real intercept, but this time you set the imaginary component to 0 and solve for omega. In this case, it's only 0 when omega equals 0 or omega equals infinity. And since we've already plotted both of those points in step 1 and 2, there's really nothing else to plot. It only crosses the real line at the beginning and at the midpoint. So now that we have this information, what does it tell us? Well, we can start with our pencil at the starting point and trace through the imaginary crossover, and then through the real crossover if there is one, and then end at the midpoint. And then we can continue on by reflecting this about the real line, and we would have an approximate drawing of the Nyquist plot. And from this plot we can see that the closed loop system is stable, since remember there were no open loop poles in the right half plane, and there are no encirclements of -1. Of course, this method doesn't tell us whether the plot looks like this or this, but it does help us to determine closed loop stability. I'm going to plot this in MATLAB and see how close we got. The first thing I'm going to do is set our system's transfer function, and then I'll plot the Nyquist plot, and here it is. And we did all right. It doesn't look exactly the same, but you can see that it starts at 0.5 on the real axis, loops down, crosses over the imaginary axis, and then ends at the origin, and the system is stable like we predicted. Now, a more complex transfer function is difficult to do in this method because you'll have several imaginary and real crossings. But if you're trying to assess a complex transfer function, you'd be better off using a computer to draw it rather than estimate it by hand. And I'm going to show you an example of this at the end of this video. So now the question becomes, what happens if you have an open loop pole on the imaginary axis? Well, let's start with a single pole at the origin, 1 over s. I'll draw the Nyquist contour and pick a point to analyze somewhere up here, and we're going to do a thought experiment. What if we bring this point on our contour closer and closer to the pole? What happens? Well, the phase stays the same at 90 degrees, but the magnitude of the phasor gets smaller and smaller. And since we're dividing by a smaller and smaller number, the magnitude in the w-plane tends towards infinity. And once we're right on top of the pole, the gain goes towards infinity since we're essentially dividing by 0 the length of the phasor, and the phase becomes what? Well, it's undefined. It's sort of all angles at once and yet no angle at all. There is no phase since this phasor basically disappears when the point is on top of the pole. In the w-plane, we basically have a point that lies out at infinity but with some undefined phase, so we're out of luck with understanding what that means. We can't use our original Nyquist contour with poles on the imaginary axis, so what do we do? The solution, I think, is ingenious. Let me zoom in on the pole here so you can understand what we do. We know that the contour can't lie directly on the pole, otherwise the solution is undefined. So why not move the contour over slightly just in that one spot? Since we just moved in an infinitesimal amount, we've accomplished two things. The first is that we're still guaranteeing that we haven't accidentally let another close-by pole escape the contour. And the second thing is that we no longer have this indeterminate solution. The gain stays at infinity since we're dividing by a really small number still, but the phase for our phasor very clearly starts at minus 90 degrees and loops around to plus 90 degrees. So now we can draw the Nyquist plot for this system. When we start at omega equals 0, you can see visually that the gain is infinity since the length of the phasor is 0, and the phase is 0 degrees. And then as we loop around the pole, the gain stays at infinity, but the phase in the W plane sweeps down to minus 90. Then as the contour continues up the j omega axis, the gain in the W plane goes to 0 since the length of the phasor goes to infinity. And finally we can complete the Nyquist plot by just drawing the reflection about the real axis. And we can say that the closed loop system is stable because there are no open loop poles in the right half plane and no encirclements of minus 1. But since you now understand the Nyquist criterion pretty well, you can easily see that this adjustment of the Nyquist contour works by expanding it in the other direction also. If we move it slightly to the left instead of to the right, the gain is still infinity. But now the phase starts at minus 180 degrees, and then just like before, loops down to minus 90 degrees phase, then up to the origin, and then finally reflected about the real axis. And even though this Nyquist plot looks different than the one we drew before, we can still say that the system is stable because we have one open loop pole in the right half plane, or inside our contour, and one counterclockwise encirclement of minus 1. Therefore 0 closed loop poles in the right half plane. Both methods work as long as you keep track of it. It's pretty awesome, huh? So what about an open loop 0 on the imaginary axis? Well, you don't really have to worry about that, because even though the phasor is still undefined in phase, it turns out that we don't really care because the gain is 0. And like I said before, when gain is 0, the point lies at the origin in the W plane, and so the phase doesn't really change that. You can do the loop around thing like we did before, but you're going to find you're going to get the exact same answer as not doing it. So for open loop zeros, proceed as normal, and for open loop poles on the imaginary axis, do this fancy adjusting of the contour. Let me show you what happens in MATLAB when you try to plot the Nyquist plot for a system with open loop poles on the imaginary axis. You get this vertical line, but you can see that MATLAB doesn't really know how to handle plotting infinity, so it just doesn't even try. In order to determine stability, you have to mentally complete the plot, swiping either clockwise or counterclockwise at infinity. And this can be tough to visualize. But luckily, even though MATLAB can't plot it well, it will still tell you if the closed loop system is stable. And in addition to that, there's this awesome plotting tool by Trond Andresen called nyklog.m. His script will handle infinity very nicely. Plus it tells you the closed loop stability and other bits of information. You can find this script at MathWorks' website, and I've also included a link in the description if you'd like to download it. So for this final example, let me show you where the Nyquist plot really shines, and that is when the open loop plant has either poles or zeros in the right half plane. Fighter jets are required to maneuver very quickly. This gives them the edge in dogfights. But a really stable airplane doesn't want to turn very quickly. Therefore, engineers have found the best way to accomplish this is by making the open loop airplane slightly unstable, or making it want to turn and pitch on its own, and then stabilizing it using fly-by-wire feedback control. The unstable plant for the pitch system of an F-16 fighter is the following, where the input is the angle of the elevator and the output is the pitch angle of the aircraft. Now you've been tasked with designing a pitch tracking autopilot system for the F-16, and you want to see if unity feedback alone is capable of stabilizing the system. You can tell that the open loop system is unstable just by inspection by looking to see that there is a negative in the characteristic equation. But I can use MATLAB to see where the open loop poles are for this system, and that's by finding the roots of the characteristic equation. And you can see that there's one just barely in the right half plane like we suspected, so the open loop system is unstable. Let me first plot the Bode plot of this system and see what closed loop stability information we can get from it. And it's a bit hard to read. Even if I show stability margins in the normal sense, you can't easily tell if the closed loop system is stable or not. And in some open loop unstable cases, you can't tell at all. Therefore, in this situation, you'd be safer just to plot the Nyquist plot instead. And if we do this, you can see very easily that there are two clockwise encirclements of -1. And since there's one open loop unstable pole, this means that there is a total of 3 closed loop unstable poles now with unity feedback. So that's not a great design. So a little bit more work needs to be done. But we were able to see that very clearly using the Nyquist plot. Alright, well that's all I wanted to cover for now. I hope you're starting to see the benefit of Nyquist plots, and hopefully they aren't as impossible to understand as you might have previously thought. In future videos I'll cover gain and phase margins with Nyquist, Bode, and the root locus methods. Don't forget to subscribe so you don't miss any future videos, and thanks for watching.
بعد كده ننتقل للسؤال الأول زي ما هو باين قدامكم على الشاشة. المعادلة n تساوي z minus b. طالب تعريف ال n وال z وال b. هي عبارة عن ايش؟ السؤال الأول ال n اللي هي number of clockwise encirclement of -1 and 0 point. Z اللي هي number of zeros of 1 plus j of s of s in right hand plane. ال B اللي هي number of balls of open loop characteristic equation. وهذا هو الحل بشكل اوضح زي ما باين قدامكم على الشاشه. وننتقل للسؤال الثاني زي ما باين قدامكم على الشاشه.
السلام عليكم. نرجع السؤال الثاني. شوف السؤال الثاني الآن. طالب في السؤال الثاني ادانا ترانسفير فانكشن، طلب منا ان نرسمها نسوي لها مابينج. اوكي. طب هذا عندنا الرسم حقتنا ونسوي لها مابينج، لازم نطلع الماجنتيود والفيز. تمام؟ طيب اول شيء نيجي من هنا نفكر في الفانكشن حقتنا. طلع من هنا زيرو اللي هو يساوي دبل.
الحين هذه ترانسفير فانكشن
ايش
هذا اللي فوق.
نيجي نطلع ايش؟ نرسمها هنا الزيرو حقنا. بعدين ناخذ كل بوينت من هنا مثلا اللي هو واحد. نعوض كل مالي. نسالب واحد زائد اثنين يطلع لك هذا الناتج اللي هو ماجنتيود. تمام؟ ناخذ مثلا مثال هذا. ونجي نطلع الماجنتيود حقنا. عندنا 2 زائد جي يساوي جذر 2 تربيع زائد 1 تربيع 2 فاصلة 2 اللي هو ماجنتيود. عشان نطلع الفيزر يكون كان انفرس 1 على 2 اللي هو يساوي 26.5. ونعبي الجدول وبعدين نرجع نرسمها بعد ما سوينا مابينج في الاف وفي الاس. وهذا السؤال اللي خلصناه زي ما هو موضح عندنا في الشاشه.
القيم هذه حقت اللي تحت ولا حقت اللي فوق؟ القيم اللي في الجدول اللي فوق حقت اللي تحت ولا حقت اللي فوق؟
اللي هنا إذا الحين عندك زيرو هنا تمام؟ تاخذ الزيرو هذا مع ليش؟ مع البوينت هذا. البوينت هذا كم؟ ماينس 1. تروح تعوضه هنا مثلا ماينس 1 زائد 2 طلع 1. الفيزر تقسمها على بعض والثاني انفرس طلع لك بس هنا طبعا الزاويه معروف اللي هي زيرو. الرسمه هذه بعد ما نطلع الجدول هذا كله تروح تعوض الرسمه هذه البيانات اللي في الجدول هنا. يعني مثلا شوف الماجنتيود لو كان في هنا مثلا زيرو
عكس الطواف بالساعة.
مع عقارب الساعة.
عكس الطول بس ما عقارب الساعة. شوف لو كان في هنا مثلا بول هنا في بول هنا راح يحسب، بس لو كان في زيرو هنا ما حيحسب. طيب سؤال ثاني. الحين ننتقل على السؤال الثالث زي ما هو موضح قدامكم في الشاشة.
ما في شيء بكرة.
زي المقارنة نفس السؤال الماضي بس ان الاف اس تغير عندنا الان اس. الخطوة الأولى نشوف نجيب الاف اس عندنا 1 0. كيف تكون الصفر هنا؟ الحين نعوض بالنقاط المطلوب منا في الاس بلين، نعوض في الاف اس حتى نرسم نسوي لها مابل. نعوض بالنقاط -1 جي سالب جي حنعوض فيها في الجدول هنا. النقاط من 1 إلى 8 حنعوض فيها عندنا الماجنتيود قيمته 1 لأن عندنا 1 0 فتكون قيمة الجدول دائما الماجنتيود ب1. والكيس عندنا المعادلة الثانية الكيس هناخذ كل النقاط نعوض فيها وحتطلع لنا الجدول التالي. والحل الأوضح مبين معكم في الشاشة.
ننتقل للسؤال الرابع اللي هو باين قدامكم على الشاشة.
وبسم الله ننتقل على السؤال الرابع. عندنا هنا ترانسفير فانكشن نفس السؤال اللي فات. ترانسفير فانكشن عندنا هنا انبوت كيف؟ هنا طلعنا انبوت. يكون عندنا انبوت هنا قوة الدائرة. يصير عندنا الماجنتيود كله بواحد. في البول هنا نعكس الحكاية. يصير عكس يصير كذا ماشي. فتطلع الزاوية عندنا بالماينس في البداية بعدين تطلع بالموجب. نفس الطلع الثاني ينبرس طبعا. في هذا طلع بالثاني والماجنتيود دائما يطلع بواحد وهذا البوينت نطلع منه ناخذ هذا يعني هذا اللي هي بعدين نسوي له ماجن ويطلع بالشكل وكذا انتهينا من السؤال هذا ونشوفه مع بعض كذا موضح عندنا في الشاشة وننتقل على السؤال الخامس.
السؤال الخامس زي ما هو باين قدامكم على الشاشة. بعد كذا ننتقل للسؤال الخامس. عندنا الرسمة هنا. الكي تجمع بين الرسمة أقل من سالب 1 0.75. طالب الجين مارجن يساوي 1 over k ويساوي 1 على 0.75 ويساوي 1.3. بوزيتيف جين مارجن لأن الكي بوزيتيف أقل من الماينس 1. بس هو الحل بشكل أوضح زي ما هو قدامكم بالشاشة.
باقي سؤال.
السلام عليكم. الآن نبدأ السؤال الخامس. زي ما مبين معنا جي اتش اوف اس 50 على اس زائد 3 في اس زائد 6. يمكن الشك اذا سيستم ستيبل او نوت ستيبل. الخطوه الاولى نجيب البولز حق السيستم. عندنا البول نجيبها من هنا، عندنا الصفر وسالب 3 وسالب 6. نسوي له بلوت على زين. عندنا هنا السالب 3 وسالب 6. الخطوه الثانيه نجيب البي والان. البي عدد البولز في الرايت هاند بلين، يبقى ما عندنا اي بول سوليد. والان عدد السيركمنت حول السالب 1. عندنا 1 2. نحول بالقانون زد ان زائد بي 2 زائد 0 يساوي 2. إذا حيكون السيستم انستيبل لان بين الزد تساوي 2. وحل اوضح زي ما بين معنا في الشرح. ننتقل للسؤال اللي بعده.
السؤال السابق زي ما باين قدامكم على الشاشة.
ثانية معليش أنا بسم الله ننتقل على السؤال الأخير. رقم 3 السؤال الأخير. عندنا هذا الجيب اتش طلع منها البولز، فعندنا هنا أول بولز هنا زيرو، من هنا نطلع 3، من هنا نطلع 6. تمام؟ نيجي نرسمها هنا، نحددها من زيرو، هنا 3، هنا 6. جينا شفنا كم عدد البولز هنا في الرايت هاند، هسه جبنا هنا، هنا عندنا 2. عدد الان، عدد اللفات على سالب 1. كم لفة؟ عندنا لفتين. نزلت وجدنا أول قانون هذا نوجد 2 زائد 2 يساوي 4. السيستم هنا شوية مستيبل. كذا كنا انتهينا من هذا التوتوريال، وهذا الحل زي ما هو موجود قدامكم. السلام عليكم.